rod's partially immersed in a fluid. So there are a couple of things you need to know. First of all, the buoyancy. So it's the weight of fluid displaced, and then because it's a weight is mass by gravity. Mass can be written as density by volume, so the buoyancy is the density by the volume by acceleration due to gravity. And because we're looking at weight of fluid displaced, the density in this case is the density of fluid, and because it's the weight of fluid displaced, the fluid is displaced by the amount of the object that's submerged in the fluid. So instead of volume of the object, we have volume of the object submerged. And in this case, the rod is not fully submerged, so the buoyancy is only due on and because of the amount of the rod that is submerged. So here's a diagram. We have a rod AB. Now I'm going to say the point where it goes into the fluid is the point C, just there for argument's sake. So the volume from A to C is what causes the fluid to be displaced. So it's that volume, the volume between A and C, that is the volume of the object submerged. The density then again is the density of the fluid with the buoyancy, and G is just acceleration due to gravity. All right, where does the buoyancy act? Well, it acts at the midpoint of the rod beneath the fluid. So there, and it acts up. We also need to include the other forces in the system, one of which is the weight, which acts at the midpoint of the rod AB. And the other one here is if it's touching off the top surface of that container, there must be a force. Now, that force we're going to say is directed vertically up, and that's because both B and W have no horizontal component. So the force at B should also have no horizontal component. If it did have a horizontal component, it would mean that the rod would be accelerating left or right in the direction of that horizontal component. Okay, let's have a look at the distances then. So if I was doing this question, I'd say the length of the entire rod is 2L, because then the way it acts a distance L from both A and B. So you're dealing with whole numbers, or you're not dealing with fractions basically. You also need the amount of the rod underneath the surface of the fluid, so I'd call that 2x. And what we know is the distance of the buoyancy from A along the line of the rod is equal to x. So the buoyancy acts at a distance x along the rod from A. And the other thing we know is if we were looking at the distance from B, the distance of the buoyancy from B along the line of the rod would be 2L minus x. I've also labelled an angle A there because all those forces are vertical, which means we'll be dealing with horizontal distances when we're calculating via the moments. And to calculate the horizontal distances, you'll be using the sine of the angle multiplied by the hypotenuse, which would be L in the case of the W force and 2L minus x in the case of the B or buoyancy force. So again, the distance of A to the line of action of the buoyancy is x sine q, or x sine A there. I forgot to change the A to a q. And the distance from the point B on the rod to the line of action of the buoyancy is 2L minus x by the sine of the angle at the top right hand corner, which is q on the left but is A in the diagram. It should be the same thing. So let's have a look at a few questions. We start with this one. We have a thin uniform rod AB is in equilibrium in an inclined position in a container of water. The end B is supported by the edge of the container as shown in the diagram. The relative density of the rod is S. Find in terms of S the fraction of the length of the rod that is immersed in the water. So what we're looking for is the length between A and C, that point where the rod just touches the water. And when we're looking for the fraction of the length immersed, we're looking for that length, the length AC, divided by the total length AB. Okay, so the first thing you need to do is put in your forces, as we had in the second slide, I think it was, or the first slide. We have the forces there, the three of them, 2 up, 1 down. And the other thing that I would do here is I would draw a second diagram and I would draw in the lengths so that my diagram doesn't become cluttered. So the length AB they're saying is L. I would suggest 2L personally. And the length AC they're calling X. I would call 2X. And the question is looking for X over L, essentially. That's what we're looking for. All right, so we'll take a turning point. That's the second line of that new slide. or that new image. The turning point is taken at the point B, so it's going to be W by a half L, which is the distance from B to where the W acts, multiplied by the sine of theta, which gives me the perpendicular distance from the line of action of W at the centre of gravity. And that's equal to B multiplied by its perpendicular distance, which is L minus a half x, and then multiplied by sine theta. Now, the way the marking scheme does it is different to the way I would do it. I would use two facts. I would use the density formula. I would use the buoyancy formula, which is rho vg. The buoyancy is the weight of fluid displaced. The fluid is water, meaning the density is 1,000. The v there is the volume of the rod submerged, which can be written as the length x multiplied by its cross-sectional area. So v is xa essentially, multiplied by g. And I'd rewrite w then as the density of the rod, which is 1,000 times the s value, multiplied by its volume, so it's the total volume, and its total volume is the total length multiplied by the cross-sectional area. So if I put the b value and the w value into that second line, which is b multiplied by, in brackets, L minus a half x by sine theta is equal to w by a half L sine theta. If I put b and w in there, I would get the line in the last piece of that box there. X all over SL, all multiplied by L minus a half x equals a half L. Now, that's a quadratic. So that's the bottom box again. So that's a quadratic, and it will give us the quadratic there in the bottom box. X squared minus 2LX plus SL squared equals 0. What you need to do is use the minus b formula. You'll get two values for x. X equals L minus L into the square root of 1 minus s, and x equals L plus L into the square root of 1 minus s. You need to take the negative version because we know that x is definitely less than L. So the negative version there is the only version that will give us the x is less than L. And then because we're looking for x over L, we're looking for the fraction submerged over the total length. Take out a common factor in that line, which is L, and divide under by it. So x over L gives me 1 minus the square root of 1 minus s. Okay, one thing that you need to note here, the second picture there has an x squared minus 2lx plus sl squared equals 0. And there's a temptation here to either make x the variable or L the variable. And the thing you have to remember is the length is fixed. The x value is the variable here. So the quadratic is with respect to x, it's not with respect to L. So what you shouldn't do is have SL squared minus 2LX plus x squared equals 0, and then use A is equal to S, B is equal to minus 2x, and C is equal to x squared. That would be incorrect because L is a constant and it is the x squared which is the variable in this case. So we order it in decreasing powers of x, and the A, the B, and the C respectively are 1 minus 2L and plus SL. Okay, I have 3 more questions to do. They're almost identical, so they may go a little bit faster. All right, we have a uniform rod, length 2 meters, and weight W is freely hinged at the point P. So there's a hinge at P, and because the buoyancy is up and the weight is directly down, the reaction or the force at P will be vertically up. The rod of relative density, that is free to move about a horizontal axis through P. The other end of the rod is immersed in a liquid of relative density 0.9. The point P is 0.4 meters above the surface of the liquid. It's in equilibrium. The angle there is theta. Find the length of the immersed part of the rod. That'll be almost identical to the previous question. And the value of theta. Okay, so the buoyancy will be the density of the fluid, which is 0.9 by 1,000, multiplied by the volume, which will be the length of the submerged portion multiplied by the cross-sectional area multiplied by g. The weight of the object will be the density of the object, which is 0.756 by 1,000. The volume of the object will be the total length, which is 2 meters, multiplied by the cross-sectional area, and then we'll have a g then as well for getting the weight of the object. And then it's much the same as the previous one. So like I said, B and W are those values. I would use the moments with the turning point at the point P. You get W by L sine theta is equal to B multiplied by 2 minus X over 2 sine theta. Now in this case, they've said the length of the rod is 2L. So the length from P to where the center of gravity is along the line of the rod is L. And then we multiply by sine theta to get the component that's perpendicular to the weight. The B value then, the total length of the rod is 2. And you can see from the diagram they said the amount submerged is going to be X. So 2 minus a half X multiplied by sine theta is the perpendicular distance between the buoyancy, the line of action of the buoyancy, and the point P. What I would do here is I would sub in the two formula that I have in the bottom left hand corner for B and W. Things would cancel. They do it differently. And you'd get the third line in that new box, x squared minus 4x plus 3.36 equals 0. Again, x is a variable, so your quadratic in x. Solve the quadratic, you get two values. One will be greater than 2 meters. That's not going to happen because it's a partially submerged rod, so the x value has to be less than L. And then to get the theta value, what you need to do is say that the x value is 1.2, so that means the amount of the rod above the water is equal to 0.8. And then we have an adjacent and hypotenuse for a triangle that would be formed, let's say, above the water by the rod. Cos of that is equal to a half, theta is equal to 60. Okay, next question. I'll leave you read that if you don't need to pause it. Same method. In this case, the buoyancy is equal to the weight of fluid displaced. That means we're looking at the density of the liquid, which is water, density of 1000. The volume is the volume of the submerged section of rod, which is X, which is the length submerged multiplied by A. And then we're multiplying it by G. The weight then is rho Vg as well, but the rho, or the density, is 1000 times the relative density or the specific gravity of the rod. So it's S in that case, multiplied by the volume, and the volume is the total length multiplied by the cross-sectional area, so 1.5 by A. You take the turning points at P once more, and that's the fourth line down, and you'd sub in what I have completed there in the bottom left-hand corner for B and W, and S solves as 5/9. The final part then is the reaction at the hinge, and this is what I mentioned previously with regard to the weight and the buoyancy being vertical. So that means the reaction must also be vertical. And the second line in that new box basically says that B plus the reaction up equals the weight. You sub in your value for B and you solve for the R. Should be fairly straightforward. If you're wondering where the B comes from, what I'm doing is writing B in terms of W, or comparing the B and the W on the left hand side and showing that the B value is 3S over W when you put one of them over the other. Okay, last question. The algebra is a little bit harder in this, but everything else stays the same. So get your B value. The density of the fluid I'm saying is Q. That's the sigma, which is like the O with the line off it, multiplied by the volume of this submerged rod, which is X, the length submerged by its cross-sectional area, and then W is rho Vg, where V is the total length of the rod, 2L multiplied by its cross-sectional area. Take the moments about A, sub in your values, rearrange it, and you get a quadratic with phi x squared minus 4L phi x plus 4L squared rho equals 0. Fill those into your quadratic formula, and remember you're using the minus in front of the square root, and that ensures that the x value is less than the total length of the rod.